Morning, everybody. Welcome, welcome. Tomorrow is the Center of Mass Lab. So you should have the lab packet for that already. I handed those out during the exam autopsy. Going to be some lecture tomorrow, right? Right at the beginning, talking about center of mass, what it is, how to calculate it, and then we'll do the lab on it. Today and Thursday is chapter 9 because next Tuesday is review, right, for the exam that's happening on Thursday, a week from this Thursday. So, yeah. Has anyone gotten an email about evaluating me? You guys have received nothing? Well, that's a different issue. Okay. I will follow up on getting that done. Okay. This is the hard bit. Like really, I mean, of this unit, this chapter is huge. So I'm hoping, it's probably not true, actually I know it's not true, that chapter 8 is done and dusted for you in the homework so you can concentrate on chapter 9, because this is where like everything is going to happen. And we need to jump right in and start talking about what happens when forces rotate. Yeah. Right? We did kinematics. We spent a whole chapter just on kinematics. We're going to lump Newton's second law, energy, and momentum toolboxes into one chapter. The good news is it's a lot like tearing off a Band-Aid really fast. The bad news is it's a lot like tearing a Band-Aid off really fast, right? The pain is more intense, but it lasts for a shorter time, right? I need a volunteer. Drew already did it last time. We need somebody else. Yeah, sorry, Drew. Come on up, Andrew. What's that? We're gonna spin to win. Should I put little things on the wheel that says like no homework, double homework, extra hard exam? Yeah, right. Okay. Thank you, Andrew. Andrew, will you please spin the wheel? All right. Did you all notice what Andrew did to spin the wheel? Do it again. Grabbed it and went which way with it? Darren, can you spin the wheel the other way? Okay. Yeah, so what direction is Andrew applying a force? Either down or up, right? Andrew's grabbing it over here, right? But it's a down or upward force. Can you spin it from the top of the wheel? Again, which way was the direction of the force? He pulled towards himself. He kept his hand going, right? Okay. But strictly speaking, if you just grab the top and just pull sideways, not down, don't follow it, just pull sideways. Let go. Try it again. Short amount of time, right? He can get it to turn, right? Just by giving a sideways force at the top, right? So Andrew knew from experience he had to apply a tangential force to get the rotation to happen, right? Okay. All right, Andrew, step right there, okay, brace yourself. What I want you to do is I want you to put your hand right there on the wheel, okay, and I want you to push towards the center or axis of the wheel as hard as you can. Go, keep going, right? Okay, you can use both hands if you want. There we go, okay. So no matter how hard Andrew pushes, the wheel doesn't spin, right? Why not? It wasn't tangential, right? Everybody give Andrew a hand. Excellent job at spinning the wheel. Please sit. Let me ask you another question. This is going to bother everybody that's coming in late. When I come up to this door, where do I push on it? Over here? Can the door be opened if I push here? Yeah, it takes a lot of effort, right? Okay. But if I push out here, you can almost do it with one finger, right? Okay. So, why? It has something. So did you notice what direction the force was for me to open the door? If this is like the door, right? You got the hinge of the door. When I came out here, I pushed perpendicular, right? from the axis of the door. Wheels are not doors, Mr. Balogh. How can you do this? This is a hobbit hole. And I have a problem. The doorknob's in the wrong spot. Why is the doorknob in the wrong spot?
They use magic to open the door.
Where do you push on a door? At the point that's furthest from the axis of rotation. This doorknob's right in the middle of the door. Two problems, right? Okay, number one, why do we put the handle next to where it latches?
Because it's the easiest point for it to open.
Yes, but that's not the first reason. You only need a bolt that long to get the door to latch, right? How long a bolt do you need in this door? Right? Okay, it's clever for fantasy, but bad for mechanics, right? Okay, and in fact, if you watch the movie Lord of the Rings, you'll see on the exterior sets all the doorknobs are in the center, and on the interior sets where they needed the doors to function, all the doorknobs are on the edge. Continuity person wasn't paying attention. Okay, and I am a fan of Lord of the Rings, just for the record. I just point out inconsistencies in the lore. Torque. Remember that we're going Greek, right? So torque is rotational force, right? It's the force that causes rotation, if you want to think about it that way. So when we had Newton's second law, in its linear form, it looked like that, right? Ma equals sum of the forces. And we had all those terrible free body diagrams and having to set coordinate systems and all that. Well, guess what? All of that's back. All of it and more. Because we're going to replace the force with the sum of the torques. That is the Greek letter tau. Tau is supposed to be like, it kind of looks like that. It's got like a little kind of wiggly. But usually in physics, all we do is do that. It's like a T. So a T is where it sticks above the crossbar, right? But a tau, we just do a T and don't go above the crossbar. Okay. So that's the symbol for torque. It's a rotation. It's something that causes rotation to happen. We know that rotation happens because the object accelerates angularly. I never know when to stop that word. Right? But if something is going to rotate, it's going to change its angular velocity, which is an angular acceleration. So that's alpha. These are vectors. Okay. And then there's another thing I need to teach you, which I'm going to teach you later, and that's rotational mass, capital I. That's called moment of inertia. Again, we're going to get back to that full description of torque here in a little bit. We're going to take a little bit of a detour where we're going to do some static equilibrium, which we've done before. We've done situations where things are hanging and there's no net force acting on them. Now we're going to throw in torque. I was going to say for fun, but it's not fun. But torque, kind of by definition, right? Remember, just like Ma isn't a force, Ma is related to the sum of forces, torque isn't I alpha. You can relate moment of inertia and angular acceleration to torque, but a torque is a force times what your book calls the lever arm. And this is a technical term that means the distance from the axis of rotation. This is how your book does it. I often write torque as R and then kind of an upside down T and an F. That notation right there isn't old-fashioned. It's actually getting more and more popular. But it means that upside down T right there means perpendicular to. It's the perpendicular symbol, right? those two lines are perpendicular to each other, right? They make a 90-degree angle with each other, okay? And so that upside down T between two things means perpendicular to. Yeah?
What is the fancy L for again?
It's lever arm. And it's the same idea, just in a different symbol. So like if this is a board or the top of a door or a rod or something, and it's pinned down on one side where there's an axis of rotation, it has to rotate around this point. And we apply any kind of force to this. Let's say a force gets applied, I don't know, like that, right? The lever arm, this is where it gets tricky, okay? The problem with lever arms is that they have to be perpendicular to the forces. So we do something called the line of action of the force. This dotted line represents the direction or line that the force is acting along. Your lever arm technically has to be perpendicular to that line of action of the force, which gets you kind of off in space somewhere. It works fine. I'm not saying it's not right. It's just I found that the concept of a lever arm can be very difficult to sort of picture or see or understand. Because what does exist and what is easy to see is the distance from the axis of rotation to where that force is acting. Okay? This is what I call R. Distance from the axis of rotation to where the force is acting. But if you're going to use that distance, remember R is not necessarily a radius. It's a generic distance in physics. I think I've said that before in this class. What has to be true about R and the force? They have to be perpendicular to each other. And is my green R and my blue force, are they perpendicular to each other right now? No. So what do we have to do? We have to find the components of F and find the one that is perpendicular to the distance. So we'd have to know the angle, right? And would we use sine or cosine to find the perpendicular component of force? Why sine? It's this side, right? This side right here is not touching this angle. I cannot defend nor can I explain why physics textbooks do this. They, almost all of them, abandon this skill that we've hammered into you of finding the components of things, right? They just abandon it and start talking about lever arms and stuff, okay? We don't need to reinvent the wheel here, okay? The distance between the axis of rotation and where the force is happening is R. It's just a distance. You'll find it, okay? And then you just, if your force is not perpendicular to that distance, find the component of the force that is. We've done that a ton, right? Why get rid of that skill? So this is why I personally prefer to write R perpendicular to F. It reminds me that if it's not perpendicular, I've got to find the perpendicular component. But let's say, for example, that we have this purple force that's acting like this. Do I need to worry about angles now? No. It's 90 degrees already, right? So I can just find my R, and there's my F, and this torque is just going to be R times F, right? Whereas the blue one, the torque would have been R times F sine theta. It's a distance. It's just the distance from the axis of rotation, okay? Whereas lever arm technically needs to be perpendicular, right? So for the purple one, is R and L, are they the same thing? Yeah, because it's perpendicular, right? The lever arm has to be the perpendicular distance to the line of action of the force. So I apologize, all textbooks do this. Again, in my professional opinion, I don't know, it's because engineers do lever arms, I think, but none of you are going to be engineers, so it's still not a good justification. So So torque is distance and force perpendicular to each other. And what happens, I'm running out of colors. What happens if the force is not perpendicular to the distance? The torque is 0. Remember when Andrew came up and pushed on the wheel towards the center? Was there any rotation? No. Was there a lot of force? Yeah. But was there any rotation? No, there was no torque to be had. Okay? So torque causes rotations if you've got a perpendicular piece of it. Okay. So we're gonna do static equilibrium. This is like the full deal now. We did a little bit before. Now we're going to do the whole enchilada. Static equilibrium. Does anybody remember what we just said about static equilibrium before? There was a really special condition. It had to do with like hanging objects off of ropes or something like that. Well, there was tension in there, but something had to be 0. Do you remember what it was? The acceleration had to be 0, right? So when you add up all the forces, they have to equal 0, right? If the acceleration is 0, add up all the forces, they're 0. Now, for the true static equilibrium, the angular acceleration will also be 0, which means we should be able to add up all the torques and also get 0. So these are the true conditions, now that we understand rotation a little bit, that we can set for static equilibrium. What do you want the net force on the Golden Gate Bridge to be at all times? 0. How do you know the net force on the Golden Gate Bridge is 0? Careful. True. But what is it that is 0? The acceleration. Do we want the bridge to accelerate? No, because if it's accelerating, what is it going to be doing? It's stationary right now, but acceleration means that what's going to happen? It's going to move, right? Remember, acceleration is a change in motion. Do we want the motion of the bridge to change? Do we want it to go down, up, left or right, forward or back? By definition, we want the bridge to stay put, right? So we want any and all forces. Is there normal force here? Are there tensions? Is there wind force? Yeah. Are there wave force? Yeah, all that stuff. We want always for all of those forces to add up to 0. What does it mean for the torque to be 0 on the Golden Gate Bridge? We don't want it to change its rotation. What's its rotation right now? Nothing, right? Do we want it to start spinning? Some of you are like, no, right? Do we want it to spin around one end or any other end or through the middle? No.
If there was rotational force, would that mean that there is potential energy causing kinetic?
We're going to do rotational energy on Thursday. Yes, the answer is yes, right? Right? Kinematics in rotation, yes, right? Forces today in rotation, yes. Energy in rotation, yes. We have rotational kinetic energy. We don't have a new form of potential energy, so you don't have to worry about that. But we do have a new form of rotational kinetic energy. And then also on Thursday, we're going to do angular momentum. Don't try to imagine what an angular collision looks like. You'll get it wrong. It's not what you think. This is a picture of Manhattan, New York, Manhattan Island, New York City, and some of the boroughs. What is vitally important that all of those buildings do? Remain in static equilibrium, right? Civil engineers, the engineers that are responsible for making sure buildings are strong enough and roads work and all that kind of stuff. What is the goal of a civil engineer? Static equilibrium. Make sure that all forces and all torques add up to 0. So let's do a problem. This is the worst. This is as bad as it gets. So hold on tight, okay? I will draw the picture for you, even though there's only words. This is, again, another skill that requires practice. I'll do my best to give you pictures when I can, okay? So, we have a horizontal beam. And we have a sign that's hanging from the end of the beam. No, that's not a, don't ever vote me for president. If I am ever running in a political race, you can know that the aliens have arrived and they have taken my body. Because I would never in my right mind be a politician, right? You would not want me to be president. First executive order, sweats are considered formal attire for all events, weddings, funerals, whatever. Second, all SUVs are now considered illegal. I don't understand. A sport utility vehicle is an oxymoron, right? It's either a utility vehicle or it's a sport vehicle. It is not both, right? If you want more about my platform, too bad. This is a physics class, not a political one. Okay, here's a wall. I don't know why I drew it as a dotted line. It's not a dotted line. Sometimes we denote like a solid surface just by trying to indicate that like there's material there, right? You don't have to get that fancy. Okay, if there were a pin right here, we'll draw like a little circle thing right there. It's like holding onto the bar at that end. If this is all there was, what would happen? Right? It would just fall, wouldn't it? Okay. So there has to be this wire that holds it up, right? Okay. And they gave us some information here, right? We know the mass of the beam, the sign. The wire doesn't have any mass, but we do know the angle that this thing is at, right? And they want us to find basically every force that's in the problem, okay? The wall force, the tension force. Usually this is what's going on. If you have anybody in your life that's a civil engineer, this is basically what they do all day long, okay? Is they add up forces and they make sure they're all zero. So why would it be important to know the tension in the wire? Yeah, think like an engineer, right? You need to be able to pick the right kind of wire to do this setup, right? So if you calculate the tension, you find out the tension's like 2,000 newtons, right? What do you want to make sure about the wire you actually use to hang it? It's stronger than 2,000 newtons. And usually engineers like have a safety margin that they're trying to work in, right? And all that kind of stuff. So they do a lot of design parameters to make sure that, yeah, if Mr. Balogh comes along and hangs off of this thing, it still won't break, right? So, but anyway, the concept here that I'm going to teach you, okay, is how to survive a problem where everything adds up to zero. Doesn't sound like it's too bad, right? Everything's zero? You can do this? Just hold on. Again, I'm ripping the Band-Aid off really fast here, right? You already know how to do the first half of the problem. So let's go back to chapter 4 and 5. Let's draw a free body diagram. What are we going to draw a free body diagram of? We've got a wire, we've got a sign, we've got a bar, we've got a wall. Technically the earth. All of them would be a bad answer, and that's actually what civil engineers do. But for us, we're going to draw a free body diagram of the thing that connects all the things. I like to call it the central actor. If somebody's climbing a ladder, let's say like a ladder is leaning up against the wall or something like that, right? You've got the wall, you've got the ladder, you've got the person, you've got the ground, you've got the earth. What is the object in that system that connects everything together, that everything is interacting with? It's the ladder, right? The person doesn't interact with the wall directly, right? The ground doesn't interact directly with the person, But the latter does interact with the ground, the wall, the person, and gravity, the earth, right? So when you are asked to do a statics problem, look for the thing that connects all the things, right? The central actor of the problem. In this case, it's the beam, it's the bar, right? It's the wall, it's the tension, it's the sign, it's the earth, right? They're all doing that. Okay, so we're going to draw a free body diagram of the beam. Before, when we drew a free body diagram of anything, what did we do for a picture? Like, how did we represent the object? Square. As a square or a circle, some simple representation, right? Can't do that anymore because torque cares about where the axis is and where the forces are acting. So for the first time in this class, we are doing something called an extended object. Up till now, every object we've ever worked with might as well have been a point particle. We never worried about the dimensions of the object. When we threw things in the air, when we slid them down hills, there was no mention of like how long the skis were that the skier was using or any of that kind of stuff. And we are now moving into a regime where we actually have to start worrying about that kind of stuff, right? And so what does that mean about the complexity of the problem? I've been saving you this whole time, and now I can't save you anymore. We just have to do it. So what are we going to do? We are going to set up a template again, right? We need to apply Newton's second law, but in the statics version, right, where the acceleration is 0. And we need to set up Newton's second law in the rotational form. So we're going to develop a template, okay? The template will consist of x and y for the linear version, and we're just, instead of writing ma equals, we're going to write 0 equals. And then over here, we'll get to this one later, but we're going to do torques. And it's also going to be 0 equals, and then we're going to get the torques down. The stuff in green will be new for today. The stuff in red, this is stuff we've done before. So let's just get the stuff in red out of the way. We need to find all of the forces that are acting on the beam. Name a force that's acting on the beam.
The wall.
The wall, okay? We don't know which way the wall is pushing. They don't give us any information in the problem. So I'm just going to go and assume it's both like vertical and horizontal. How did I know it had to be like out and up and away from the wall? Because I've done a lot of these problems, right? Okay. There's more sophisticated ways of coming up with this, but you want to think about how this thing would want to twist, right, at the wall. Like if that pin failed, right? It's hanging, right? The pin over here fails. What's it going to do because gravity's holding onto it?
Go down.
It's going to like go down, right? So that means the wall must be holding it up, right? And pushing out. So we'll have some checks here in a second, but I'm just going to do wall force. Okay, what other object is pushing or pulling on the beam? The sign. So I'm going to do mass of the sign, m sub s times g. MSG. I like MSG. MSG is actually not bad for you unless you have an actual sensitivity or allergy to monosodium glutamate. The whole idea for MSG being bad for you is actually based in racism and a pushback on Asian cultures moving in the United States in the 1950s. White people took a direct link between MSG and food, and it would make you sick so that the Chinese businesses wouldn't compete, but it's all a lie. What does MSG do for food?
Tasty.
Yeah, makes it taste good, right? Your fried chicken tastes good because they put MSG in it, right? Monosodium glutamates. Glutamates are the umami flavor. It's what makes things taste meaty. So mushrooms have a lot of monosodium glutamate. Like mushrooms are sometimes called the meat of the vegetable world because they just have this like kind of unctuous quality to them. A good steak, fried chicken, whatever, those all have glutamates in them. There's more monosodium glutamate in there's more glutamates in turkey meat than like basically anything else, which is why people like turkey. Anyway, there's your cultural education for the day. Oh yeah, MSG. What else? Good. Tension in the wire, which is going to act along the wire, isn't it? So I'm going to draw it kind of up like that. Are we missing anything? Think of all the objects. Remember I asked you to think about, back in the day I was teaching you. Think about objects, think about objects, think about what objects are pushing or pulling on the beam?
Gravity on the beam.
Yeah, we have the earth, right? It can be sometimes easy to forget. That's m sub b times g. Again, I'm just doing the weights of the beam and the weight of the sign, okay? They don't tell me that the beam is uniform, but I just assume that anything, if you're not told where the center of mass or the center of gravity of an object is, just assume it's in its middle. All right, more on that tomorrow. Okay, so I've got all of the forces. Before I can write down forces in the x and y direction, what do I have to do? We need an axis, right? Now the axis, what are we going to do here? We got options of keeping it sort of straight and normal, right and left, up and down. We could tilt it. Like, what's your feeling here? Just keep it? Yeah. Usually I try to line my axis up with my, my central actor, my object. Okay. In this case, I'm going to call right positive x, and I'm going to call up positive y. But in choosing that, 2 out of my 4 forces don't play nice. Two of them actually are already in the y direction, aren't they? So which ones are they, Ella? Those are the ones that play nice. But the 2 you were saying, tension and the wall, they have components, don't they? X and y pieces. So we got to go find those. So for tension, it points up and to the left. I'll call this one Ty, I'll call this one Tx. And the wall force, it points to the right and it points up. I'll just call them Wx and Wy. I know there's an angle in there. I come back later and figure out what's going on. I'm just going to label those components as they are. X and Y. We'll get sines and cosines in later. This is already hard enough. Just stick with X and Y. Okay, so now that we've identified all of our forces, which isn't a guarantee, but again, think about objects, all the objects that are pushing or pulling on the central actor. And we've identified the components of things that need components in our coordinate system. We now go to the template and we start filling it out. In the x direction, what are my forces? You're looking at a line right along here, and you're just looking at every force that's in that line. So what are they? Wx and Tx, right? Now you go back and do the directions. Wx, positive or negative? Tx, negative. Okay? All right. In the y direction, we're now going to start looking vertically all along the bar. We're going to look vertically, right? So what's a vertical force? Wy, mbg, ty, and yummy, msg. Did we get all of them? There's one there, and 2 at the end, right? Is that all of our vertical forces? Yeah. Okay. You might want to put check marks on your diagram. Okay. Are we done? No, we forgot the directions, didn't we? So what are the directions? Wy, mbg, ty, msg. Okay. So that should be the familiar part. There's nothing really in there that's any different from what we've done before with chapters 4 and 5. So again, there's review in here. There's review built into this. Don't despair. You're like, oh, I sucked at chapter 4 and 5. I still don't understand it. Here's another chance, right? It's in these problems again. More practice. And I'm hoping that if you haven't gotten it before, that maybe some of it will start clicking now. That's ideal, of course, but you never lose the feeling that you have no idea what you're doing in physics class. one of the hardest things that human beings have ever come up with, physics, right? So you all always walk out of here going, I have no idea what just happened. But I hope you walk out of here understanding that I believe in you and that I believe you can do it, right? That's more important. Even as this looks so complicated, and you're sitting here probably on your third time through the video at this point, right? Hi, future you, right? Still trying to come to grips with this. I know, I got you. Okay, we got to do torques now. And I very cleverly put all of those components in green. Why did I do that? We'll leave it in green. It's fine. Okay. For torque, and here's the new part. You got to pick two things. You have to pick an axis of rotation. Is this object rotating? No. We don't want it to rotate. But we are still going to pick an axis so that we can define torques. We can pick this axis wherever we want. We have that power. So here's a rule of thumb. Pick the point that has the greatest number of unknown forces. The wall is one point where we've got two unknown forces, right? Wx and Wy. Is there any other point that's got the same number or more unknown forces acting at it? The tension, where the sign is, right? Because there's also two unknown forces over there. Tension X, tension Y. Mr. Balogh, your rule of thumb didn't help this time because they're equal. Well, then pick either one. It doesn't matter at that point. I generally, if there isn't one that's standing out to me as the point of greatest number of unknowns, I just pick the one that makes more sense to me. And I think, well, this is going to be the pivot point if the wire breaks, right? Probably the wire would break before the pin at the wall broke, right? So if it doesn't matter, I'm just going to pick the one on the wall. And that's what we're going to do. So make sure that you define your axis, right? You got to have some way of indicating where your axis is on your diagram. You can draw an arrow and say axis like I did. You can put an X on it. You can put a dot, like something, right? Something that future you can come back and say, oh, okay, that's where I picked my axis of rotation. Again, is this a real axis? No. Okay? If this is a wheel, then it's pretty obvious. You just pick the center, right? Because that's the thing that it spins around. But in equilibrium problems, it's not always so simple. Pick the point where the greatest number of unknowns is. And if you've got equal points, pick the one that you like better. Once you pick, it doesn't matter if you picked right or wrong. What matters is that you pick and stay consistent with your choice. We're going to define all of our torques from this point. But if we did it at a different point, we'd actually come up with the same equations. Even if they look different, they'd actually be the same. You just have to trust me there because you don't want to go through that exercise. Trust me on that. Just pick a point, see if it works. If it doesn't, you might need to go pick a different point. We're going to pick the axis on the wall. In addition to the axis, pick a direction for positive rotation. That direction is either going to be clockwise or counterclockwise. So what do you want to have it be? Clockwise or counterclockwise for positive rotation? Clockwise? That kind of surprises me sometimes. Yeah. Counterclockwise is typically the direction of positive angles, isn't it? Start at the positive x-axis and work your way up counterclockwise. We're going to go clockwise today. I want you to see that it doesn't matter what direction you pick. What matters is that you stay consistent with your choice, right? It's consistency that matters, not what you actually chose. And by consistency, I mean obeying your choices. If you say something's positive and it's rotating that way, then make it positive, etc. So first step with the new torque stuff. Define an axis and a direction that you're calling positive. This is exactly the same as setting up a coordinate system, right? Without an x and y, it's really hard to do forces. Without an axis and a rotation direction, you can't do torques. There's no way to get any kind of grip on what's going on. Okay, second step, identify all the torques that you have. Now that an axis has been chosen, we have to go and we have to see what forces are causing torques. And so we're just going to march through our diagram and look at every force we've got and ask a question. Does it create torque? Not what it is, but does it create torque? WY. Does WY create torque if the axis is right there and WY is right there? No, why not? There's no distance, right? Torque needs a distance in order, like a lever arm or a distance perpendicular, and we don't have any of that. What about WX? No. Why does it not have any torque? No distance. Both of these forces got wiped out in our torque equation because we put the axis where the rule of thumb said put the greatest number of unknowns. That's where you put your axis, because it makes those unknown forces have zero torque. You're like, but usually you're trying to find that. Yeah, you're usually trying to find everything. So wipe out the biggest number of unknowns first, and then work through it. I'll show you what I mean by that. So WY, WX, no torque because they have zero distance. Okay, what's the next force I run into? MBG. Does it have torque? It has distance from the axis, and even better, it's perpendicular, isn't it, to the distance from that axis? So what I'm going to do over here is I'm going to write torque sub MBG. It's just a symbol. Don't worry about the math yet. We're just trying to get ideas down on the page. WY, WX didn't have any torque, but MBG does. Okay, our next force is TX. Does it cause torque?
No.
Why not?
No distance.
Oh, it's got distance. The axis is here, but TX is, but it's parallel, right? This is the same as Andrew trying to push on the bicycle wheel, right? Okay. If you're pushing directly towards the axis, there can't be any torque. Torque requires a perpendicular force, right? And TX is not perpendicular, so it doesn't cause any torque. All right, what do you want to do first, TY or MSG? TY. Does TY cause a torque? Yes. It's got distance from the axis, and it's perpendicular, right? So we're going to write that one down. Leave a space, torque due to TY. Okay? What about MSG? Yep. Same reason. It's got distance, and it's not pointing directly at the axis. Okay? Okay, what do you think the next part's going to be now that we've gotten down those three causing torque? We've got to get the directions. So here's a trick to help you get the directions correct. Okay? Take your pencil, pen, finger, blood vein, whatever it is you're using to write with. Hold it so that it is your central actor, in this case the beam, right? So you'd hold it perfectly horizontal. Grab the end that you said the axis is at. And with your other hand, you're going to apply forces. So let's do MBG first, the weight of the beam, right? Which way is the weight of the beam applying force? Down. So you can either pull it down or you can push it from above down. But the thing is, your force is down, right? With my finger grabbed onto the left-hand side of my pencil and I pull it down, which way is my pencil rotating? Clockwise. And what did we say about the clockwise direction? So that just caused a positive torque. Do TY right now with each other, right? Do TY. Use your pencil. Good. I'm seeing a lot of people grabbing it on the left side. You come all the way to the end and you push up, right, for TY. Or if you want to, you could pull it up. Either way, which way is the pencil turning? counterclockwise. The pencil rotates counterclockwise. So what are we going to put down for that one? Negative, right? Okay, M sine G. Positive, right? So do that like kinesthetic exercise, right? Don't just stare at the page and go, I don't know. Take your pencil, line it up with your central actor, and then just start applying forces to it, right? Whatever direction the force is acting, pull it that way, see what happens. You're isolating each one. You're not trying to think of all of them at the same time when you do this. You're just looking, okay, MBG, what is that one doing? Okay, TY, what is that one doing? Okay, MSG, what is that one doing?
So just so I'm getting a kind of picture, we first identified the most unknowns, just so we could take those out of the picture.
You got to develop an axis and a direction for positive rotation.
It doesn't have to be necessarily like quote unquote correct.
Nope,
Consistent.
just consistent. Okay, second step, identify what is causing torque and get the directions. I kind of split those up. List out my torques, right? And then go back and get the directions. The third step is to write down what the torques actually are. We've just used the symbol tau here for torque, right? But what is a torque? A torque is a distance perpendicular to a force, right? I'm going to use Mr. Balogh's version, right? Your book would say lever arm. I'm just doing this, okay? So this means for every tau, we have to figure out the distance and what the force is. So for this equation right here, it's going to be plus, we already did the sign, the torque for MBG. What's the distance from the axis that MBG acts? It's half the length of the beam, isn't it? So if I call little l the length of my beam, okay, and I divide it by 2, then that's the distance. What's the force? It's just MBG. Kind of handy, the subscript you use for your label for the tau, for the torque, is the force that we're talking about, right? Okay, and then where does this minus come from? The line above. I'm just writing the line above and I'm filling it out, right? So the signs are just coming from the line above, right? So what's the distance to TY? It's the entire length of the bar. And what's the force? TY. What's the distance to MSG? L. And what's the force? Can I run that back? You can later on YouTube. Yeah, no, I hate to do that to you, but I've only got a certain amount of time, and this is a big chapter, right? So this is I'm going kind of quick here, okay? The red part hopefully feels somewhat familiar. The green part should be what's freaking you out. It's the new stuff. It can be difficult. So go back, watch this, go over it. Practice with the problems in the homework, right? Practice getting those torques down. You're going to make a lot of mistakes. Learn from those mistakes, right, as you go through this. Key things, right? Where is your axis? What direction is positive? Without those, you really can't talk about torque. Once you've got those defined, what's causing torque? And what are they, positive or negative torques? And then writing down distance and the perpendicular force. That's what you want to do. That's your algorithm. You run that over and over and over again until something comes out. I don't even remember what are we being asked to find? Tension and W, right? Now it becomes a math puzzle, a math problem. What am I looking for? I need W's and T's everywhere, don't I? T right there, okay. Does anybody see a path forward? I don't know Wx, I don't know Tx, so I can't use that equation. I don't know Wy and I don't know Ty. I can't use that. Why can't I use the equation?
Unknowns.
There's two unknowns in one equation, right? Does anybody see an equation that only has one unknown in it? The torque equation. All it has is Ty in it. Right? We know everything else, don't we? I set this problem up cleverly. This is just me being cute. What happens to all the L's? There's an L in every term, isn't there? So here comes math. This is 1/2 mbg minus Ty plus msg. The L's all canceled out, right? So Ty moves over, becomes positive. I have 1/2 mbg plus msg. I know all those numbers. I can go find what that is. I found it to be, I didn't write it down. Yes, I did. 490 newtons. When I put all the numbers in. I didn't box it. There we go. Okay. And okay. Now that I know Ty, where can Ty go for me to find something? Into the y equation. We're solving 3 equations with 3 unknowns here. Right? So I solved the Ty equation. Ty looks like it's going to be equal to msg plus mbg minus wy. I think I did all of that math correctly. I don't care if I did or not, because this number is going to be correct. I'm sorry. I've already lied to you. This was not 490. This, what did I just solve for? This is 490. What did I did it all wrong. I wanted wy is what I wanted. Wy is msg plus minus t. There we go. I just flipped my symbols around. This is what happens when you do too much algebra in your head. So wy is going to be equal to that number, which is 98 newtons when I put all the numbers in. Okay, so I've got wy and I've got ty, but that's not what t and w are, right? Because t and w also consist of their x components. How do I find like tx if I know ty? Cosine. Yep. I got to remember that I've got t and I've got tx and I have ty and an angle. What's the relationship between y and x? If you don't know the tension, it's tangent, isn't it? So we could find tx directly from that. We could also, since we know ty, and we know ty does not touch the angle, that's got to be t sine theta. So we can find the tension. Turns out the tension in the wire total is 855 newtons. That came from the that equation right there. Since I know ty, I can solve for the tension t. Tx was 700 newtons. Okay, and then that's just a number for along the way. Could you have also found tx and then done Pythagorean theorem? If you have ty and tx, can you just do 700 squared plus 490 squared square rooted? Yes, the answer is yes. So whatever way you want to do that, lots of different ways to do it. Okay. I know wy. Now that I know tx, what do I know about wx? They're the same. Wx is equal to tx from this equation up here, right? Which is then means that that's 700 newtons. And I probably find w by doing square root of 700 squared plus 98 squared. Square rooted, which I did, and I got 707 newtons. Angle, 8 degrees by using the inverse tangent. I did a speed run of the mathematics. I spent most of the time in this problem in the torque stuff because that was the green. That's the new stuff, right? As far as I'm concerned, black is math. And so I went really fast and did a lot of shortcuts because this isn't a math class, okay? But what are you taking away from this problem that has taken us 45 minutes? An hour? When did we start this class? We started at 9:30, right? It's 10:25 for one problem with the teacher's help. One problem. It's right? Not 7, 1, right? What's your takeaway from this?
Hard.
This is hard, right? This is hard. Okay, it's peak difficulty for this unit, right? Luckily, it's all just happening sort of in one situation, in one part of a bigger chapter, right? Okay. I don't want to tell you to give up. Don't give up, but realize that there will be 6 other questions on the exam. This will be one of them, something like this, a static equilibrium problem, right? I will engineer the problem so that I think that you can do it in 10 minutes. If I can do it in 2, you can do it in 10. Okay? I can simplify the math part. I can even arrange the problem so that it's more conceptual in nature. Like I could give you a diagram and then write down a torque equation for that diagram and ask you to tell me what's wrong with the equation. What do I want to see that you know?
What torque is it?
Torque, how to know when the torques are balanced. These are the physics parts, right? You will get into some hairy math for your homework. Let AI do it or struggle through it, whatever you want. I will make sure on the exam that if you do get some math, it won't be hairy. It'll be like one equation, one unknown. Because you don't have time to waste on an exam with doing lots of bad math. You're still required to know math. You still have to do it. Still got to get an answer, right? But I've got ways to be able to test you on this. So as you're trying this stuff and doing the harder versions on your homework, keep in the back of your mind, okay, I need to know what torque is. I need to know how to write it down. I need to know how to use it and identify it when it's positive and negative. Yes, Wiley Plus wants to know an answer, and you're going to get mad that it's red all the time, right? We can work on that part together. But the focus isn't the math, it's the physics. And I have ways of finding out whether or not you know the physics. And I know a lot of you are like, Mr. Bailey, please just ask us math. That would be so much easier, and you're not wrong.
So it says 710 newtons. What's the piece below that?
Theta equals 8 degrees.
Theta equals 8 degrees.
I'm terrible at handwriting, and I was starting to move fast because I wanted it to be done. I don't like this either. There's a reason I am not a civil engineer. This is mostly it. Did not want to do this for the rest of my life. Okay. It feels fast. You'll have several homework problems on this. Do your best. Use those as ways to practice learning about torque. But we need to move on and deal with situations when there isn't static equilibrium, when something is changing its rotation. And this comes back to how I originally sort of wrote down, right? This analog, right? That's the linear version. And the rotational version has the rotational symbols in it. Remember, we just go Greek. The capital I is not Greek, but anyway. Moment of inertia. This is scary. This doesn't look good, does it? Now you just kind of look at that and you go, huh? What role is capital I playing up here? Like, what's the analog to the linear version? It's mass, okay? Moment of inertia. We're going to do a lab on moment of inertia next week. Moment of inertia is rotational mass. And what does mass do normally? Like if something has a lot of mass and you want to throw it, what do you know you need? A lot of force, right? So mass gives you an idea of how much force is required to change or accelerate an object, change its motion. Moment of inertia tells you how much torque you need to get something to spin. It's like resistance to rotation. Mass is resistance to motion. Moment of inertia is resistance to rotation. The thing about moment of inertia, though, is it entirely depends on where that mass is located. For example, if I take this meter stick and I hold it in its very center and turn it. Do you see how I can just turn it with my fingers? Right? Really just kind of no effort here. I can just kind of keep it spinning. Okay? If I now grab it by one end and I try to turn it with just my fingers. Try this at home, like grab a broom, right? Okay? Try to spin it through its center of mass. It's much easier than if you try to spin it from one end. Okay? Did the mass of this meter stick change? No, but what changed? Where the moment of inertia changed, but what changed was where the mass was in relation to the axis of rotation. Holding this meter stick at the end means there's a whole lot more mass further away from my axis of rotation. It takes a lot more effort to get this one to rotate. Whereas here I'm splitting the difference, right? The mass has moved closer to the axis of rotation, so it's easier to spin. Meter stick in the center has less moment of inertia than a meter stick rotated around the outside. Mass didn't change, but the axis did. In general, moment of inertia is mr squared. That's a generic moment of inertia for any object that is rotating at a distance from an axis of rotation. So what's the moment of inertia of this tennis ball? It's mr squared. Okay? It's the mass of this ball times the distance the ball is from the axis of rotation. For a kid on a merry-go-round, what's the kid's moment of inertia? Mr squared. Because the kid is sitting on the edge of the merry-go-round, is at a distance from the center, and going around on the merry-go-round.
So this is always playing into effect that it's always equal, like the example you did.
Not always. Case in point, this table. This table is going to become your best friend. This table, this exact one, will be on the exam because it's a reference table for all the moments of inertia for complicated objects. Mr squared is for simple objects or an object that is located, like if I'm on a merry-go-round, my moment of inertia on the merry-go-round would be mr squared. Because there's nothing in the table that says Mr. Balogh at a distance from the merry-go-round, right? But this wheel has a moment of inertia. It's like a bunch of little tiny objects at a distance r, but we got to add up all of those moments of inertia together to get the total moment of inertia. So if we wanted to find the moment of inertia of this wheel, we can use this table to figure it out. This wheel consists of simple shapes. What's one of the simple shapes this wheel consists of? A thin-walled hollow cylinder. That would be the rubber wheel around the outside, right? A thin-walled hollow cylinder. Oh, that's interesting. Mr squared, right? But you notice it's capital M, capital R squared? Capital M for total mass. capital R, for the total radius, right? But that's not the only thing this wheel consists of. What else does the wheel consist of? These spokes, the supports that hold the wheel up, right? Is there a shape on this table that looks like a spoke? Yeah, it's B, slender rod axis through one end. How many spokes are there? 8, right? So we would do 1/3 the mass of one of the spokes times the length of one of the spokes squared times 8. And add that to the mr squared for the outside. But we're not done. What's here in the center? A solid cylinder. So we get the solid cylinder center mass, its radius, 1/2 mr squared, add it together. So what this table allows us to do is figure out the moments of inertia of basic shapes, but then also put shapes together to find more complicated moments of inertia. A ceiling fan, right, with that kind of central hub and all of the blades coming off of it. Let's say it had a center hub and then it had, I don't know, three blades coming off of it. Assume all those blades are equal. What would we do to find the moment of inertia of this ceiling fan? What's the central hub going to look like? Solid cylinder, right? 1/2 mr squared, that's the hub, whatever the mass of the hub is times the radius of the hub squared, half of it, right? Plus, and then there's going to be 3 of these. What do you think? Think like a physicist. And don't pick D. Yeah, everybody wants to go for like this one, right? Okay. But do the fan blades rotate around an axis like this? No. Okay, and they don't do this either. So the fan blade's actually this again. It's not a rod. It's pretty close. Okay. So I'd use 1/3 ml squared again. 1/3 ml squared, right? Where this is L, right? And the mass, they're all the same. Times 3, which I got on the front, right? That would be the total moment of inertia of the fan blade. What would you use for the moment of inertia of a basketball? Nope. Thin-walled hollow sphere. But only if the basketball were spinning on an axis, like if somebody's doing that trick where they balance it on their finger, right? What about a bowling ball rolling down the bowling lane? Yeah, that would be H here, the solid sphere. Why a solid sphere versus a hollow one?
Basketball has air in it.
Basketball's got air in it. Most of the mass of a basketball is in the rubber shell, right? Whereas a bowling ball has mass all the way through it. So they will have different moments of inertia. Is the axis of a bowling ball as it rolls down the lane look like this one? No, it is. You just turn this thing on its side, it's still going around a central axis, right? Okay. So don't get all hung up on whether the axis is vertical or horizontal. That doesn't matter, right? What matters is that the axis passes through, say, the center of the bowling ball. Yeah. Yeah.
Like in reference to like if it's the center of
Good question. Totally set me up. I did not pay him to do that, right? Okay. So anybody that's ever done pottery knows that playing on the pottering wheel can be pretty fun and really hard. Okay. Took a pottery class this last Christmas with my family, and boy, that was an adventure. I'm glad somebody was there to save me from my own inability. But we're going to take a look at applying what we know about moment of inertia and all this kind of stuff. This might go into next class. We'll see. Right? But let's see if we can knock this one out. Draw for me. There we go. Okay, so what I just drew was the top-down view of the potter's wheel. Okay? And I'm going to say that the potter's wheel is spinning around that direction. Usually from above they spin counterclockwise. I don't know why. And it's got like the axis of rotation of the potter's wheel is right in the center. And the rag, right, that the potter is pushing with is pushing directly onto the edge as the wheel goes around. Right? Here's the potter's wheel. Potter's wheel is going around, and they take their sponge or their rag and they just push directly into the side, right? So what's slowing down the wheel? Be more specific. Friction, right? Because this, what is it, 70 Newton force? Is that what it is? This 70 Newton force pushing in, right? That's like a normal force that's getting applied, isn't it? Why am I calling it normal? Because it's normal. It's perpendicular to the surface of contact of the wheel, right? The force is going in, surface of contact is right there, that's perpendicular, right? Which way is the friction going to be if this thing is rotating counterclockwise? It's going to be the opposite direction, right? So at this point where the rag is applying, would I draw that friction up or down? Try again. It's kinetic friction. It acts against the direction of motion. Which way is the wheel moving at this point? Up. Tangential to the motion, right? So against the motion, the kinetic friction which acts against the motion would be pointing down. Okay? We've got distance from the center. Okay, what do they want to know? Find the coefficient of kinetic friction between the wheel and the rag. We are going to do this. This problem is an example of using Newton's second law, but now it's not zero. Okay? Stop. All right, so we'll do moment of inertia in a second. We'll do alpha in a second. Let's do all the torque first, right? To be able to talk about torque, what two things do we need? We need an axis, right? And we need a positive direction. So, what do you want to do? Where's our axis? It's kind of picked for us, isn't it? The axis is right here. Okay. Now we need a positive direction. Do you remember what we did for Newton's second law when things were sliding down hills and stuff like that? What was our rule of thumb?
Wherever the x is, the acceleration.
Yeah, follow the acceleration, right? This thing is rotating counterclockwise, but it's slowing down. So which way is the acceleration? Alpha, and so therefore my positive direction, I want to be in the clockwise direction. You can put clockwise there to give you some help. Okay? All right. So with that, I can now write down my torque statement. How many torques are there? How many? One. Why is it one? There's two forces. There's a torque due to the friction, and then is there a torque due to the 70 Newton force? No, why not? It's parallel to the axis. That 70 Newton force is pointing directly at the axis. It can't produce torque. Remember, torque has to be perpendicular force to distance. So that's the only one we've got. And it's positive, isn't it? Kind of by definition, we said anything. How would we do this one with our pencil? My pencil's not a wheel, Mr. Balogh. What do I do? Grab at the axis, along the radius. Which way is the force acting? Down. Which way is my pencil rotating? Clockwise. Positive torque. And what is that torque? It's R perpendicular to F. What's the distance? Well, it's the radius of the potter's wheel. What's the force? The force due to friction. When friction's involved, Don't forget how fun things are. What's the only thing we don't know now? We want to solve for that coefficient, right? It's going to be I alpha divided by n. What's the only thing we don't know? Do we know alpha? Yeah. Do we know the normal force? I forgot an R. Oh, run! Run! Oh, no, sorry. What do we need to know? No, we're looking for the coefficient. But we know alpha, we know n, we know r. What don't we know? I. Where are we going to get I? From the table. Which one of these is a potter's wheel? Probably the solid cylinder, right? Okay. So I would say I is equal to 1/2 mass of the wheel, radius of the wheel squared. Go find that number, chuck it in there, put in all my other numbers, and get a mu. When I did all these numbers, I got 0.312. Again, that was a speed run through the problem because on Thursday we need to do energy and momentum in rotation. I'll see you tomorrow for the Center of Mass Lab. Have a great rest of the day. You are getting beat up right now. You should feel very beat up, right? But it's going to be okay.